This is Stefan Karlsson. He's a senior scientist at the RISE Research Institutes of Sweden, the glass unit of the Department of Materials and Surface Design. He holds a PhD in glass technology and from Linnaeus University in Sweden. And he has been granted the Former's Future Research Leader and been awarded a Marie Curie Fellowship and was coordinator of a project Solar ERANET and is also author of more than 25 peer-reviewed scientific papers. And today, Stefan will talk about towards practically stronger glass, recent advances and outlook. And this sounds interesting. So we are curious about your presentation, Stefan.
Right. Thank you very much. Yeah, a bit different for me to be here. And I will talk about a little bit different topic than previous talkers. And so I am a chemical engineer in the background, so bear with me. Anyhow, towards practically stronger glass. So first I will give some introduction to strength of glass, and then some about the theoretical and practical strength of glass, and then how we can improve the practical strength of glass, and then give some summary and conclusions. So all of you know that glass is a brittle material. So strength primarily depends on the surface and edge flow conditions. And the strength decreases with the size of the largest crack. So it's basically statistically distributed, and actually like this graph to the right, it explains very well how glass strength works. But strength also depends on the time of load, the glass composition, the environmental conditions, and the size of the loaded area. And as you can see here, yeah, it's statistically distributed, so glass can be strong, but can also be weak. And we basically have to design for the weakest. And of course, that also depends on the time scale of the load. And that's standards for this, so that's probably you know this already. So to understand strength of glass, some fraction mechanics, some basic fraction mechanics is good to know. And here I just summarize some of the important equations where I think this doesn't work. Okay, where the stress intensity factor is up to the right, the equation there is quite important to know, and all of the gradients in the equation to understand what actually affects the fracture stress of the glass. And then we have this static fatigue, where actually the subcritical crack growth also depends on the environment. So this equation is for this one. And it's about practical strength of glass. So here I show to the right 741 tests on 6mm annealed glass samples. And as you can see, it's not perfectly normal distributed, but it's it's a little bit shifted. Most of them are in the middle, but of course there are some at the lower bottom as well. And we have an average which is about 72, and the 5% fractile of 48. But I took some table from Fred Fehr as well to show. I mean, working with the materials, ideally we think if we make it thicker, then you will make it stronger. But it's actually not true for glass. So just for Fred Fehr table here, increasing the thickness, you can actually even lower the strength. Which makes glass a bit special. So So towards practically stronger glass then. And then we go down to these pieces in the equations. So we can increase the K1C, and that you can do with different glass composition or different microstructure in the glass. Or we can decrease the K10, that would mean initial defect size. And then we can decrease the applied stress, that means counteract the stress. Or we can decrease the crack velocity, the subcritical crack velocity. And that we can do with glass composition or different atmosphere, protective layers. Or we can keep K1, which is a function of the crack depth, basically, low. And that we can also do with the glass composition, optimized glass composition. So the first one, K1C, that's more towards specialty glass compositions, and that's mainly other glass industry than we are having here today. Decrease K10 is a pure glass processing problem. That's about achieving as high quality glass as possible. And then I will also talk a little bit in the end about quality sorting and how we can do that. Counteract stress, that's strengthening of glass, building surface compressive stresses. Decreasing crack velocity, then we can optimize the glass composition or apply protective coatings. And then keep K1C low. That would be damage-resistant glass. And that's what they have been doing a lot in the specialty glass industry for mobile phones and so on. So just some examples on this. Decrease K10. I mean, in all glasses, in all float glasses, I would say, we do have inclusions and defects. So you can have stony inclusions and you can have bubbles, and these will affect the strength of glass. And we basically need to get rid of all the defects. That would mean a high quality glass. Some good examples on this is Corning's fusion process. Then you would have two sides which is not affected by rollers or anything like this. That would be a high quality glass surfaces. Of course, online and inline inspection systems, but of course they also have some limitations. Also, air flotation and air cushion tempering is a good example of this. That allow us to temper thinner glass. And then laser cutting, which is probably coming more and more, is also a very good example for this, to get a high quality edge strength. And then you can also have coatings to bury the surface flaws. But I think we need also more good examples of this. So we need to develop this further. And as I mentioned, I will talk a little bit about quality sorting and non-destructive testing of glass. Decreasing applied stress. So that's basically strengthening. You know already thermal strengthening. It's a common technique, has been applied for many, many years. And lately, chemical strengthening has also been improved a lot, and I think it's becoming more and more used also in architectural applications, but mostly for special architectural applications. But these are common techniques, I would say. And then recently there has been coming up some technique where you're using hydrogen or hydration to induce compressive stress. This is a paper from Corning where they have been using this. But of course, it takes a lot of time to do this. So as you can see, treatments of 5 months in lab air and 1 year in lab air, and yeah, then you have But I think it's scientifically very interesting, and I think we can learn something from it, and then we will see how much we can use it in practice. One example, which was actually from this Solar Aeronet project that was mentioned, where we tried to combine CVD depositing of alumina and thermal strengthening of glass. So I mean, when you temper glass, then you increase the temperature to above the TG, and then you actually are at a quite high temperature. So you actually have some possibilities to do surface modification. And that gives this opportunities. So we actually deposited by CVD alumina onto the glass and then quenched it. And by this you can also achieve some better surface properties. And here is an example of the crack resistance, which I will explain a little bit more about later on. But you can increase the crack resistance, and that's basically keeping K1C low. And here is also some example on the scratch resistance, and that you can increase the scratch resistance by this. And it's fairly simple. We did this in the lab, and I think it's not too difficult to build it in a tempering line either. So anyway, we can also locally increase K1C by surface modification, and in the same time also decrease this subcritical crack growth speed. You can do this by cation exchange or anion exchange, and here is some example on anion exchange, where they have been treating the glass in ammonia at elevated temperatures, and then you can actually increase the both the crack resistance and the KC in this case, the stress intensity critical factor. And also the failure strength. So very interesting work of this. Another example of decreasing the subcritical crack velocity is given here, that you can change the glass composition. So you have soda lime silicate, you have borosilicate, and then aluminum silicate is more durable in chemical-wise. And that's a good example of this. So it's basically chemical reactions and combined with applied stress. And that's why you sometimes call it stress corrosion. And also the acidic, the pH of the environment matters. So actually, the worst cases would be to have a high pH, and then water is in the middle, that's a pH 7, and then lower pH is in fact better. So then the crack velocity starts to increase at a higher K1. And of course also the temperature matters. So increasing temperature is also worse. And that's, that's also a thing to think about when the global temperature is rising. That perhaps we will have different scenarios in the future. All right. So about coatings and protective coatings. Here is some example on low-E coated glass, where actually the low-E coating actually can protect the glass surface from atmosphere, and thereby increase the strength of the glass. About keeping K1 low, then we have something called low brittleness glass or damage resistant glass. And here again, the crack resistance, that's basically you do indentation into the glass, and then you count the cracks at the corners of the Vickers indenter. And then you get some statistics out of this, and at 50% of the load and the probability of crack initiation, you can get the crack resistance value. And by just small modifications of a normal soda lime silicate glass, you can in fact double the crack resistance. And that's pretty remarkable without changing hardness and the elastic modulus very much. So there's room for improvement, basically. And this will also affect the strength of glass in the long run. And I think those that launched this understanding about low brittleness glass and so on is this Siegel and Ito, which made some pioneering work on this. And here are some examples of images out of this, where they have designed a different composition to get lower damage of the glass with inflicted loads. All right, so non-destructive testing of glass, something completely different. I mean, measuring strength is time-consuming, it's destructive, and we need to design for the low-strength glass. I mean, envision that we could non-destructively measure the glass. What could we do with that? And I think we could push the boundaries. We can basically sort out the low-strength glass and use it for something different. And then we can use the high-strength glass for those applications where we need it. And also, for example, expensive processing and so on. And then we won't crack so much glass as we need to do nowadays. So it's a recent study from us and my collaborators. We had an idea. We needed to have some way to do controlled defects into glass. And then we found this old paper where they made indentation and they were having cracks due to high indentation load. And then you can see at the right side that you get a quite nice distribution of the strength of the glass by different indentation loads. So that was basically the idea to provide a proof of concept of non-destructive strength testing. And yeah, here again, this crack resistance, I think we went through that. Then we had 10 by 10 centimeter samples with indentation in the middle. Yeah. So this is how it looks like when we made these indentations. So we have cracks forming at the corners of the Vickers indenter. And then about this non-destructive testing, we have used non-linear acoustic wave methodology, where you are basically, when you are tapping on a material, you can actually hear if there are any defects into the material. And here we are using ultrasonics, and if there are any distortions, defects in the material, there will be some distortion of the sound. And this you can detect with transducers and receivers, and then we can actually calculate a damage value of this materials. And this works on basically all solid materials. So it's not unique for glass. It has just not been applied that much to glass yet. So yeah, so this is the setup that we had. So we are basically focusing on where we made the indentation, so in the middle. And then we can actually determine on the amplitude of the sound how much of the sample that will be focusing on. And then we did ring-on-ring tests as well on this. That's just a normal ring-on-ring test. I see I'm running out of time, but I will speed up then. Two results. We can actually, so here's the comparison of the non-destructive damage value in a normalized way, and the strength of stress at failure. And we can actually see that we get pretty good correlation. I mean, it's not perfect, but it's more than half, or more than are within 95% of the of these dashed lines. So I think it's a pretty good correlation, and this actually gives a proof of concept that we actually can non-destructively test strength of glass. Of course, there will be some stress corrosion during our strength test. So therefore, we did some calculation on how much we extend the cracks during the tests. And then we can actually calculate failure stress based on the indentation, diagonal crack length, and then we got some correlation to the average failure stress from the test, so where we account for this stress corrosion. And it's in fact quite good correlation. It's not perfect, but it's quite good. This is basically the calculations that we did for this. About details and so on, we recently published a paper on this, so you can read about the details in construction and building materials. I think I will skip this slide because, and I hope to talk to you some more about this during the conference. But this is just some motivation applications that you can use for non-destructive testing of glass. So summary of conclusions. I mean, the past 20 years, we have received a quite good and great understanding of the glass strength. We also got some new innovations, but I think there are still much we can do. And I think most promising is, getting high quality glass, optimize glass compositions, and also to keep K1 low. And then we can, of course, we're already doing this with counteracting stress by strengthening the glass. And I mean, I also think thinner and stronger glass is all in line with sustainable development to use less glass and do it wisely. Also want to give some marketing for a new paper that is coming up, a review paper. We'll be publishing together with Macrelli, Varshnaya, and Mauro. And that leaves me to some acknowledgement of funding agencies and collaborators that keeps inspiring me, and that I can learn from. So, thank you very much.
Thank you, Stefan.